Okay, section 8.1, sample spaces and basic probability. This is actually pretty straightforward. You just have to count things, which is what we learned how to do in chapter 7, and then divide in certain and then do some division. So what we will do is we will talk about sample spaces. So problems 1, 2, comma 23 through 26, 61 and 62, and then we'll talk a little bit about the probability involving rolling 2 dice, which is problems 39 through 54, and card problems. Boink. That's 3 through 20, 31 through 34, and 77 through 84. Those are all card problems. And then finally, we'll do some stuff to do the word problems. Right? And so, of course, you don't have to watch the entire video all at once. You can watch one of these 4 sections and then do the corresponding problems, and then watch the next section sometime later if you want. Okay, so what is probability? And the simplest way to think about probability is it's, you have a bunch of possible outcomes and you're interested in some of them. And so what fraction of the possible outcomes are the ones that you're interested in? So we have some notation. S stands for sample space, all of the possible outcomes. E stands for event, and that's just certain outcomes that you're particularly interested in for some reason. So the hypothesis we usually use simple events, not just events, but simple events, is that the simple events in the sample space are equally likely. So suppose you roll 1 die, right? There's 6 possible outcomes. You roll a 1, a 2, a 3, a 4, a 5, or 6. All of those are equally likely. And those are all rolling a 1, rolling a 2. Those are all simple events. There's some events that are not simple. So rolling a 2 or a 3 or a 4, right? That's not a simple event. So those are a little bit more complicated. So probability of E then is N of E over N of S. And remember that N means the number of things in a set. So the number of things in E divided by the number of things in S. So we have to count, like we learned back in chapter 7, about we have to count various things. So E is a subset of S. It's some fraction. What do we know about probabilities? Well, probability of an event, since it's a fraction, right? This N of E is always less than S, less than or equal to S, because E is a subset of S, is between 0 and 1. Or if you think of your probabilities as percentage, right? The percentage of something happening is somewhere between 0%, 0% means it's impossible, or 100%, which is certain. It'll definitely happen. Right? So the sum of all simple events in a probability distribution has to be equal to 1, or 100%. Right? Something has to happen. If you roll a die, you get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. The probabilities of those things have to add up to 1. So, as an example, Suppose you have a sample space, S is your sample space. And E is some event, and F is some other event. And you do your calculations, you figure out probability of E is 0.6. Probability of F is 0.8. Is this possible? And the answer is no. E and F are two simple events, right? Right? And so if the only two things that can happen are either E or F, and you say, well, I did some calculations, I found out the probability E is 0.6 and probability of F is 0.8. Well, if those are the only two things that can happen, and it adds up to 1.4, so that's too much. And this is, when you're dealing with sports and people keep saying, I can give 110%. It's like, no, you can only give 100%. So let's look at a more concrete example of this. Rolling 2 dice and adding up the number of dots. So one die has got 6 sides. It's a cube, right? And they've got 1, 2, 3, 4, 5, or 6 dots on the sides. So 2 dice. Well, if you add up the number of dots, right? What can you get? You can get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, right? Are these equally likely? Right? If you roll your dice, are you just as likely to get a 7 as you are to get a 2? And the answer is, well, no. You get a 7 much more than you get a 2. If you ever played Dungeons and Dragons, right, or the old school Dungeons and Dragons where you had to roll 3 dice to figure out where your characteristics, right, really hard to get an 18, but really easy to get a 12. So, this is not a equally likely sample space, right, because 12s are much less likely than 7. So we need to construct something a sample space where all outcomes are equally likely. And what we can do is set up a big table, because what we're doing is we're rolling a first die and then a second die. We know with dice there are 6 possible outcomes. 1, 2, 3, 4, 5, or 6. Oops. First die, second die. 1, 2, 3, 4, 5, or 6. So those are the possible outcomes. So if you're rolling 2 dice, a first die and a second die, what are the equally likely outcomes for the 2 of them? Well, you could get a 1 and a 1, or you could get a 2 and a 1, or you can get a 3 and a 1, or you can get a 4 and a 1, a 5 and a 1, and a 6 and a 1. These are all equally likely, these 6, right? Because you can get a 1 on the first die and a 1 on the second die, or you get a 4 on the first die and then a 1 on the second die. The roll on the first die doesn't affect the roll on the second die. So what's the rest of them? Let's see. Oh, the second one is being constant. Sorry about that. So we can get 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2. Or we can get 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. You can see how this is going to go. For each pair of numbers, we get one equally likely outcome. And so then the question is, how many possible outcomes are there for rolling 2 dice? Let's see, 1, 5, 2, 5. It's hard to speak and write at the same time when you're not doing the same thing. So how many possible pairs are there here? Well, there's 6 for the first one, and then 6 for the second one. So the multiplication principle tells us that there are exactly 36, once I'm done with all this, possible outcomes. 5, 6, 6, 6. Right? 6 across, 6 down. 36 equally likely outcomes. Excellent. And so there's our table for dice. And you can figure out what 7 is, right? This. These 6. If you roll those, you get a 7 by adding up the number of dots on the top. Right? But this is the only way to get 2. This is the only way to get 12. So there's 6 out of 36 ways to get a 7, but there's only 1 out of 36 ways to get a 12. So what's the getting a sum of 7? Probability of sum equals 7. And so what's the notation that we use here? P, and then we write some kind of event in the parentheses. So this is the probability of getting the sum equal to 7. Oops, not what I wanted to do. And what's that equal to? Well, this, that gets me 7. So 6 out of 36, which is 0.16. So 16.67%. What's the probability of getting a sum strictly less than 4? Well, strictly less than 4 means you're getting 2 or 3, right? So 1 plus 1, that's 2. 1 plus 2 is 3. 2 plus 1 is 3. So these 3 events. So that's 3 over 36. And 3 over 36 is 0.0833. Right, which you can change to 8.33%. What about a probability of the sum less than or equal to 11? Well, this is a little bit tricky, right? The sum less than or equal to 11, let me use my red pen here. This is 11, these are 10, these are 9, these add up to 8, 7, 6, 5, 4, 3, 2. So less than or equal to 11, well, it's everything but 12, right? And there's only one way to get a 12. So one of the very useful things in doing any kind of probability is the idea of a complement. The complement to sum less than or equal to 11 is, of sum less than or equal to 11 is sum is greater than 11, right? Because either the sum has to be less than or equal to 11 or has to be greater than 11. But sum greater than 11, that's just saying you want your sum equal to 12. So what do we know about complements? Well, the sum of everything being less than or equal to 11 plus the sum of everything being equal to 12, those two things together is everything in the entire sample space. So this is 1 minus the probability that the sum equals 12, which is 1 minus 1 over 36, which is 35 over 36. And I hadn't calculated what that was. So let me just write that up real quick. 35 divided by 36. 0.9722. So complements probability of an event plus the probability of its complement equals 1, or of course 100% if you want to do your complements in terms of your probabilities in terms of percents. So probability of E plus probability of E prime equals 1. So the complement of sum less than or equal to 11 is sum equals to 12. Right? So these two things have to add up to 1. So this must be 1 minus probability of sum equal to 12. So that's a useful thing to know. Okay, card problems. We've done a number of these, so we will just, let's see if I can do this, paste. There we go. There's a deck of cards. We've seen this a couple of times. 4 suits, hearts, diamonds, clubs, and spades. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King. These are called ranks. There are 4 suits. 2 of the suits are red. 2 of the suits are black. And these at the end are called face cards. Great. So, when we're dealing with cards, right, and we should note that card problems are problems 3 through 20, 31 through 34, 77 through 84. So when we're dealing with card problems, that's the deck of cards that we're dealing with. So, a couple of different probabilities. Pick one card, for example. One card at random. How many choices do you have at total? 52. Right? And so your sample space is just these 52 cards. And you pick one and you see what you get. So what's the probability of getting a number card? Right? Well, there's 9 number cards. 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? These are number cards. So there's 9 number cards in each suit. So there's 36 of them total. And there's 52 cards in the deck. So N of E here, the number of possible outcomes that you're interested in, that's 36. And 36 over 52 is 0.6923, or 69.23%. So if you're picking one card at random, there's 52 possible choices. If you want a number card, there's 36 possible choices for a number card, so 69.23%. Probability of a jack or a spade. Well, you have to be a little bit careful here. And let me go back to my red pen. Here are my jacks. And here are my spades. So, put a quote here. N of E equals the number of ways, the event that we're interested in is jack or spade. But we know from the addition principle that that's the number of jacks that you have plus the number of spades that you have minus the overlap, number of jacks and spades. Oops. Right. So or is a union and is the intersection. So this is going to be 4 jacks plus 13 spades minus the one card that's a jack or a spade. So that's 16. So what's the addition principle in action? Well, if you want to count up all the stuff that's circled in red here, what do you get? Well, you have these 13 plus these 4, but you don't want to count the overlap twice, so you subtract 1 off. So there's 16 possible. So what's the probability of drawing a jack or spade? It's 16 over 52. And the 52 is because there's 52 possible cards. And that's 0.3077, 30.77%. Okay. The second type of problem are poker hands, and we'll restrict ourselves to 5-card hands. And we're assuming that, of course, you have a random, well-shuffled deck, so you dealt 5 cards at random. So the probability of any particular hand is the number of ways to get the hand divided by number of all hands. So what's that? Well, what's a poker hand? There's 52 cards and you're just choosing 5. And remember, when you're dealing with a poker hand, the order that you get the cards in doesn't matter, right? You're just worried about what 5 cards you have in your hand, not whether you've ordered them in a particular way. So that's C 52-5. So when you dealt 5 cards at random, the denominator you have will always be C 52-5. So probability of getting 5 black cards. Right? And so what do you need to calculate? Well, the number of ways you can get a hand that is 5 black cards over the number of all possible hands, that's C 52-5. For this, remember that there's 26 black cards, right? And you want to be able to pick 5 of them. So this becomes C 26-5 over C 52-5. And that is 0.025, or 2.5%. This, incidentally, is 2,598,960. That's how many possible hands there are in a deck of cards. And 2.5% of them have 5 black cards in them. So, in calculating any kind of poker hand, you figure out how many ways there are to get the hand, and then you divide by the number of all hands, which is the C 52-5. So what's the probability of getting 4 of a kind? Well, you have to calculate the ways there are to get 4 of a kind. Oops. Or 4 of a particular rank, and you have to divide it by the total number of cards. So what is that? Well, if we're going to do 4 of a kind, what do we need to do? You need to pick a sequence of cards. Let's do this down here. 4 of a kind as a sequence. What do you do? Well, step 1, pick one rank from 13. What kind of 4 of a kind do you want? Well, do you want 4 aces? Do you want 4 jacks? Do you want 4 kings? Whatever. So that's choose, out of 13 you choose 1. And then you pick those 4 cards from that particular rank. So C44. Great. Now you've got 48 cards left. Because it's a 5-card hand, and you have to pick 1 card out of 44. And so there's 624 possibilities. four of a kind hands. Right? So pick what rank you want, pick all four of those cards, and then pick one out of the 48 that's left. So probability of four of a kind is 624 over C 52.5, and that becomes 0.00030 zeros, 24. 3 zeros, that means 0.024%. Four of a kind is very rare, less than 1% of the time. 2 kings, 3 queens. Well, probability of getting exactly 2 kings and 3 queens, which is one of the types of full houses you can get. Probability is always the number of getting 2 kings and 3 queens over the number of all possible card hands, poker hands. Right? And so we need to calculate this thing on top. We know this thing on the bottom will be C 52.5. So 2 kings or 3 queens. Again, we need to think of this as a sequence of operations. Pick 2 kings. And there are 4 kings, so you need to just pick 2 of them. And then you pick your 3 queens. And there's 4 queens, so we pick 3 of them. This is the number that you picked. This is out of how many? 4-2 is actually 6. C4-3 is 4, so there's 24 possible hands that are 2 queens, 2 kings and 3 queens. So the probability of getting 2 kings and 3 queens is 24 over C 52.5, and this entails lots of zeros. 0.00, let's see, 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. And 9, 2, 3. 9, 2, 3. And I need this thing to go away. There we go. So, or, well, if there's 5 zeros for the percent, then you need 3. 2, 3%. Okay. So, any kind of poker hand, right? Whenever they say, what's the probability of getting a 5-card hand, your denominator is always going to be C 52.5, which is this big number. And then you just need to calculate whatever event there is, how many different ways there are to get that. The other type of card problem is that they pick 1 card at random out of a deck. That means you only have 52 choices because there's 52 cards. Okay, and the last batch of things are like the word problems, and this deals with which were the word problems? 89 through 92. And we'll spin all the way back down. 89 through 92. Okay, so here's a problem that's a lot like 91. 7 women, 9 men have applied for 4 positions. Right. If these are filled at random, right, and so we're assuming basically that the way the hiring process goes is that you have a set of qualifications, a bunch of people apply, and in this particular application process they got 16 people who meet the qualifications. And so if they're filled at random, what's the probability of getting 3 women and 1 man? Well, as always with the probability, I'm going to abbreviate women by W and man by M. It's the number of getting the event that you want, 3 women and 1 man, over all possible ways you can get that. So all possible outcomes, you're picking 4 people out of 16, right? There's 16 applicants, 9 plus 7 is 16, and you're only going to be filling 4. So 16, 4, that's all possible outcomes. How many possible outcomes are 3 women and 3 men? So that should be an N there. Well, first you need to pick 3 women out of the 7 that applied. And then you need to pick 1 man out of the 9 that applied. Right? And that's the number of ways that you can get 3 women and 1 man. And that's 35 times 9, which is 1820. So there are 1820 possible ways to pick 3 of the 7 women and 1 of the 9 men. So the probability of 3 women, 1 man is 1820 over C16.4. And C16.4 is, no, that's not right. C16.4 is 1820. Sorry about that. This is 1820. Got my notes screwed up. And 35 times 9 is 315. Great, so the probability of getting 3 women and 1 man is 0.1731, or 17.31%. Excellent. So, what's the probability of getting 2 women and 2 men? Well, we will make this a little bit shorter. This is number of ways to get 2 women and 2 men over C16.4, which is the number of all possible outcomes. How many ways are there to get 2 women and 2 men? Well, first you have to pick 2 of the 7 women, and then you have to pick 2 of the 9 men. So it's a sequence of choices, so it is a multiplication principle, and then you divide by the number of all possible outcomes to get the probability. And if you grind that out, you get 0.4154, or 41.54%. What about probability of getting all women? All 4 of them are women. Well, number of ways to get all women over number of all outcomes. And again, it's a sequence of choices. You need to pick 4 women out of 7, and then you need to pick 0 men out of 9. So C90. All over the number of possible choices, which is C16.4. And if you multiply that out, you get 0.0192. 1.92%. There's 1.92% if you do this randomly that you'll get all women. Oops, sorry about that. So, what's the probability of getting at least 3 women? Well, it's an interesting question. But we know what at least 3 women is. Probability of getting at least 3 women equals probability of getting exactly 3 women and 1 man, or probability of getting 4 women, because that would be at least 3. 4 women, 1 man, 0 man. So our addition principle says whenever we have an or, we take the probability of the first plus the probability of the second, and subtract off the probability of the overlap, which is an AND. But this probability equals 0, because can you have exactly 3 women and exactly 4 women on a committee? And the answer is no. You can have 3 women or you can have 4 women, but you can't have both. So probability then of at least 3 women is probability of 3 women and 1 man plus the probability of 4 women and 0 men. And we've actually calculated those. Probability of 3 women and 1 man is 17.31%, or 0.1731. Probability of all women is 0.0192, minus 0, because the probability of the overlap is 0, because it can't happen, and that's 0.1923. And that's the probability of having at least 3 women on this committee, being hired for this job. Committee problems are very similar to this sort of hiring job. Okay, so the word problems are all pretty much like that. If we go all the way back up to the top, right? What is a probability? Every example we've seen has been like this. Probability is the number of ways there is to get the outcomes you want divided by the number of possible outcomes. A couple of sample spaces that come up. One is rolling 2 dice. You'll see a bunch of that. 36 equally likely outcomes. So n of s is 36. That shows up on the bottom. Dealing with card problems. If you pick one card at random, there's 52 possible choices, so n of s is 52. That shows up in the denominator everywhere. If you are doing a poker hand, you're dealt 5 cards at random. How many